Swayam Prabha. Digital India. Educated India.
So when we are trying to do MD simulations, we saw that the most important step is to build a model for the real system that we would like to study. The success of MD simulation in predicting experimental results will depend a lot on the choice of the model and how we build it to what level of accuracy. So in this context, in this particular lecture, we are going to discuss about various model systems and interaction potentials. So now in the MD simulations, we like to represent the system by specifying it's a microstate. So what we mean by a microstate of a system is by specifying positions and momenta of the constituent particles. So what we mean by particles here, this particle could mean any constituent of the system that we want to study. This can refer to atoms or molecules, or even in some cases if you want to study nanoparticles or colloids, vesicles, micelles, and etc. Okay, any entity that you want to study, we collectively call them as particles because we don't want to switch terms like atoms, molecules, nanoparticle every time. So we'll just specify particles mean any of these constituent of the system that we want to study. So once we understand what particles are, then we would like to basically specify the positions and momenta so that the entire system can be described. Now, when we ask how do we specify the position of these particles, we make this approximation called Born-Oppenheimer approximation. For example, if you consider this argon atom, so the argon has a nucleus. It has about 18 protons and neutrons in the nucleus, and then 18 electrons in the shells. So what is shown here is the Bohr model of the argon atom. So when you say specifying position of one argon atom, what do we mean by that? Does it mean that specifying the nuclear position or specifying all the 18 electrons positions as well? Well, in the classical MD simulation that we want to do, we're going to make this approximation where we do not want to specify the electronic degrees of freedom. We are going to just look at only the nuclear positions. So the way you can model argon atom is by specifying the center of mass of this atom, which is basically the nuclear position, and then also give a size to it. Okay, so this argon atom is basically considered as a sphere of a particular size. You might wonder why we have to assign a size, because we are worrying only about the nucleus. So why should it have a size? So that you can understand by looking at, if you think about two argon atoms coming close to each other, the moment they start overlapping with the electronic shell, there will be a repulsion. So this can be modeled as an excluded volume effect. So to account for finite size of this atom, so we give a particular size centered about a nuclear position here. So this is what Born-Oppenheimer approximation means, where the positions correspond to the nucleus and all the electronic motions which are very rapid compared to the nuclear positions, we basically average them out and we represent them in a spherical model. Okay, and we also want to use a classical description of the system. What that means is, when we do this classical MD, we don't want to take into account of any quantum effects or relativistic effects or any radiative effects. Okay, so we basically look at some system where none of these effects are important. It doesn't mean that you cannot do MD simulation with when these effects are present. It's just that we have to resort to a different kind of techniques, special methods to handle. But for in this particular course, we are going to look at a classical system where the position momenta can be specified at any given point of time, which is not the case in case of quantum mechanical problems. Similarly, we don't want to talk about we don't want to consider relativistic effects because we are not talking about things that are moving at light speed and beyond. So we want to basically constrain ourselves to a very simple classical description of the system. In such a case, when you have n particle in a system, you basically specify all the positions of the constituent atoms. So q1, q2, q3, qn, these are all called generalized coordinates. This can be Cartesian coordinates like r, which has components of rx, ry, rz, but it need not be always a Cartesian coordinates. It can be of any system of coordinates which uniquely specify the position of the particles. And then we also specify this momenta, which is given by this p, which is basically a set of p1, p2, p3 up to pn. That means for each particle we specify the momentum, and momentum here p is defined as m times v, where m is the mass and v is the velocity. Okay, so these are vectorial quantities. So describing a microstate of a system essentially means specifying all the positions and all the momenta of the particles in the system. So that's what we mean by microstate. Now once we have this information in a classical description, then we can write the total energy or the Hamiltonian, which is written as this letter h, which could be a function of both q and p, coordinates and momenta, into two parts. One that is kinetic energy, the other one that is potential energy. So in this case, we have actually split the total energy into two parts, such a way that the kinetic energy is only a function of the momentum and the potential energy is only function of the coordinates. This is most of the times this works, but there are some special instances where the potential itself can be a function of velocities. For instance, if you think about Lorentz force, that is force acting on a charge moving in a magnetic field, there you will see that the force is also dependent on the velocity with which it's moving. Okay, but those are special cases. So we will consider this kind of splitting of the kinetic energy and potential energy as a single variable problems in this case. So now the form of kinetic energy is something familiar to you. So we generally write kinetic energy as half m v square, but now since we are not using v but momentum, which is p equal to mv, so that's why kinetic energy takes this form, p square by 2m. So here if you look at the summation, the first summation is over all the particles. Okay, the kinetic energy is calculated for the entire system, so we have to account for the all the particles contribution to the kinetic energy, and this alpha here basically goes over different components, vectorial components, which is x, y, z components of the momentum. Okay, so this pi alpha basically means the alpha component of the ith particle's momentum, and mi here is the mass of the ith particle. And similarly, the potential energy is given by this v of q, and this basically encodes all the intermolecular or interatomic interactions between the constituent atoms. So once we have described the kinetic energy and the form of potential energy v of q, then we have the total energy. With this prescription, now we are ready to write set of equation of motions in any of the following framework, namely Newtonian or Lagrangian or Hamiltonian. Okay, so in other words, the starting point of doing MD simulation is specifying the total energy of the system, or in other words, this potential energy of the system. So once that is ready, then we have all the other framework to go about solving the system of equations. So thereby, the key input to MD simulation is basically through the potential energy functions. Now in this class, we are going to look at some form of potential energy functions, very simple to very complex. So now, if you look at this potential energy, it basically has multiple contributions. It comes from unibody interactions, two-body interactions, three-body interactions, and etc. So there's all this actually is now written here as sum of unibody interactions, where this I will go from 1 to n, and then two-body interactions, three-body interactions, so and so. In this particular summation, first I goes from 1 to n, and then j, that's a second index, goes from j is greater than I to n. That's because we don't want to double count every pair. So when you account for interaction between 1 and 2, you don't have to again count 2 and 1 interactions, it's already accounted for. So that's the reason why we have J greater than I symbol. Same thing goes with three body potential also. Now, if you look at what is the relative importance of each of these contributions, unibody, two body, three body and four body interactions, experience shows that the two body interactions, also known as pair interactions, is the most important contributor to the overall energy or potential energy of the system. So we could write then this V2 here, which is right here, which is the two body interactions or pair interactions. We write simply as instead of writing Ri times Ri Rj, we simply write Rij, which is nothing but the distance between two atoms or two particles I and j. Okay, so if I have particle I here and then particle j, and these are the positions. This is Ri and this is Rj. So this particular pair potential depends only on the absolute distance between the two, which is Rij, which is a scalar quantity defined as the modulus of this vector Ri minus Rj. So we can simplify or simply write this V2 of Ri, Rj as V2 of simply Rij, where Rij here is a scalar. Now, if you look at the three body contribution, that is this term, for certain for certain systems, it is found that the 10% of the energy comes from the three body potentials, three body interactions. But then if you look at the way we calculate, this is actually a triple sum over the number of particles, which is quite time consuming. In many of the simulations, we basically ignore the three body potentials because of this numerical intensive calculations. And also for the fact that it contributes only 10% or lesser amount of energy. And then if you go to the other four body and five body interactions, their contributions to the system's energy becomes even more lesser and more computationally expensive. So for practical purposes, in MD simulations, we basically define an effective potential which has only the unibody interactions and the pair potential interactions. And now if you see, I have written, instead of V2, I have written V2 effective. This is because we are trying to hope to get a effective pair body potential such that it has all the other contributions, three body and four body also. Okay, so this V2 and this V2 effective and V2 need not be exactly the same. There will be some difference because of the contributions coming from other interactions are mapped effectively onto this V2F. So in other words, this is the final expression that we want to use. In MD simulations, the potential energy depends on unibody interactions, which can be because of external field or other reasons, and then more importantly the two body interactions. So now I am even dropping the suffix 2 and the effective. So from now on, whenever we talk about V of R, we have to remember this is a pair potential or effective pair potential only. Okay, and the force calculation in MD simulation depends only on this two-way summation over number of particles. And because of the fact that this effective potential includes multi-body interactions, we may say that we might find that the parameters of this VFR, the pair potential, may weakly depend on the density and temperature. That's something we have to keep in mind because in true two-body potential, these should be independent of density and temperature. But now since we are mapping the other body interactions into pair body interactions, and then when we try to match the experimental data, we sometimes tweak the parameters of the two body potential, pair potential, and then you will see small change or small difference or variations in these parameters as temperature and the density is changed. So this is not always the case, but we have to keep in mind that these parameters could be a little bit sensitive to experimental conditions. So now we'll take some examples of very simple potentials. So now from now on, all the potential I'm going to talk about is a pair potential, okay, between two pair of atoms or molecules or particles. The most important potential is called this Lennard-Jones 12-6 potential. The mathematical form is written here. This Lj on the superscript basically means Lennard-Jones, and it depends on the distance between a pair of particles. And it has two parameters. One is this epsilon, another one is the sigma. And this R here is again interparticle distance. You can see that there are two functional forms, one that is raised to the power 12 and another one raised to the power 6. That's why this Lennard-Jones 12-6 potential means. Now if you look at the plot of this function, so you plot V Lj as a function of distance r. So it goes something like this. So initially at a very small r, the V is positive, highly positive, and then it comes down and then goes through a minima, and then it increases and then goes to 0 at a long distance. So the way you can understand this potential is that if I keep one particle here at the origin, and then if I keep another particle somewhere here corresponding to this distance, you will see that these particles do not interact because the interaction energy here is 0. But if this particle were to come closer and closer, let's say it comes somewhere here corresponding to this distance, then the potential energy between these two pair of particles would be the energy given by this particular point, which is this. Okay, so this atom is more likely to come to this position from here because as it moves to the left, as it comes closer to this particular atom, it gains more energy, so it wants to come inside, it wants to come nearby to this particular atom. And then if you continue to move this, so if you bring this atom somewhere here, so then you have at this point the energy is the maximum, okay, or energy is the minimum. So the attraction energy is the most negative here, and that's a most favorable position for these pair of particles. Now if you continue to move the particle even closer, and you can see this energy will start shooting up, and then the moment you cross this point, then these two particles don't want to come close to each other, they want to push against each other because this energy becomes now positive. This is basically a source of repulsion, and this comes because if the atoms come too close to each other, then the electronic overlap will happen, and that will try to push them back, okay, because of repulsive interactions. So that's a characteristic of the Lennard-Jones potential. So long attractive tail, this particular tail is given by this expression minus 1 by r power 6, and then it has this potential well of depth epsilon. This potential well is this epsilon here, that tells you the magnitude of attraction. And then usually this epsilon is represented in the units of temperature by writing epsilon by kb. This is because epsilon is given in joules and kb is in terms of joules per Kelvin. So Kelvin comes on the top. So the unit of epsilon by kb will be in kelvins. So when we try to represent this well depth epsilon, it is given in terms of epsilon by kb in the units of temperature. And then this potential also rises steeply the moment r becomes less than sigma. So this is a sigma, r equal to sigma is this place. Okay, the moment the atoms come closer than sigma, then this there is a sharp increase in the repulsive interactions. So these kind of model systems are very successfully used for organs, organ as a species, and you can see that the dotted line that is shown here is a Lennard-Jones potential by this expression, and the continuous line that you see here is by a potential called BBMS potential, derived based on various experimental and theoretical means. And you can see that the functional form is quite reproduced, except that there's a small difference in the epsilon values between the two. So this particular dotted line, Lennard-Jones curve, is drawn using this equation with the parameter epsilon by kb of 120 Kelvin and sigma of 0.34 nanometer. So even though there is a small difference between the experimentally predicted potential and the Lennard-Jones potential, the collective behavior of the system, the experimental results agree very well with the simulations, at least for liquid organ. So this is one type of potential, and then we have also very many number of idealized potential. So they are not very realistic from experimental perspective, but they are very useful in conducting some simulation of some simple systems, sometimes even to test theories of liquid state theories. So despite their unrealistic nature, doing simulation, computer simulation of such a idealized simple model is very easy. And if you want to start MD simulations, you start with this simple potential and then go on to more refined and sophisticated potentials. So the first one we want to talk about is what is known as hard sphere potential, and the mathematical form is given here. This Hs here means hard sphere. So when the particle separation r is less than sigma, the potential is infinite, and the moment r goes above sigma, then the potential is 0. So graphically it is shown here, V of r in the y-axis, r in the x-axis. So you can see that this is r equal to sigma, Okay, so when r is greater than sigma, the potential is actually 0, as you can see here, but the moment r equal to sigma, then the potential goes to infinity. That means two sphere cannot really interpenetrate each other. They are like hard billiard balls that cannot be pushed against each other. Okay, so that's the way you can think about hard sphere potential. And so in this case, there's only one parameter, which is sigma, that determines the size of the atom or the size of the particle and their interactions. The other idealized potential is called this square well potential, and pictorially it is shown here, V of r versus r. So here, when the particles are far away from each other, the potential is 0, and then there is a range in which the potential has a well. Okay, and then the moment the pair of particle comes closer than this distance, then the potential goes to infinity again. So mathematically it is shown as when r is less than sigma 1, so this is sigma 1, this point is sigma 1, it's here. So when r is less than the sigma 1, the potential goes to infinity like a hard sphere. But then the moment r is between sigma 1 and sigma 2, that is in this particular region, then the potential is minus epsilon. Okay, so that's an attractive well, and a pair of particle wants to be in this particular well because that's the most stable configuration. But the moment that this pair of particle leaves this r value, that is when r is greater than or equal to sigma 2, so from here onwards the potential goes to 0. So this is another characteristic of a square well potential. So apart from these hard sphere and square well potential, we also have what's called the soft sphere potential, where this SS here means soft sphere, and it is represented as epsilon times sigma by r to the power some exponent nu. And in other words, you can also write this expression as some parameter a times r to the power minus nu. Now this exponent nu dictates how sharp or how steep the potential is going to vary with respect to r. So here two examples are given, when nu equal to 1 and when nu equal to 12. So by comparing these two, you can see that higher the value of nu, steeper is the potential. You can see it goes very steeply compared to this, which is more softer. So now this soft sphere potential is very much useful when you want to model very soft material like hydrogels, micelles, polymeric particles, or even grafted nanoparticles. So those ones are something which is very soft. You can really push them against each other. Sometimes they are even deformable. So in such a case, this kind of potential gives you a means of modeling such a soft material by tuning this parameter nu, and you can have very steeply rising potential or a very soft potential by tuning this value of nu. So these are some other choices we have. And another famous potential is known as this WCA, which is called Weeks, Chandler and Anderson. So these are three set of scientists who devised this potential, and this is not very different from Lennard-Jones potential. All they did is they take this Lennard-Jones potential, which we saw just now, and so this is the location of R minimum, and then if you take the derivative of Lennard-Jones potential and set that equal to 0 and solve for R, then you get R minima, and that will be the sixth root of 2 times sigma. So that is the position of this minimum. So what they do here is they cut the potential at this particular point and take this piece and then shift by amount of epsilon. So remember, the potential corresponding to this minimum is epsilon. So you basically shift this left hand part by adding epsilon. So this part goes here. Okay, so that is what's shown here. Okay, so this way is to kind of think about having a purely repulsive potential. So when you take this part and then move it up to the by adding epsilon, then you get this potential, and this is a purely soft repulsive potential. Mathematically it is shown here. This R here basically means repulsive Lennard-Jones, which is you take the Lennard-Jones potential and then you add this epsilon. That's what shifting I was talking about, and this is valid only for R is less than R minimum. Otherwise it's 0. So that's why you can see that after R minimum the potential goes to 0. So if you want to model purely repulsive system, this is one way of using Lennard-Jones, cut shifted Lennard-Jones for only repulsive. Now what is the remaining part? The remaining part was this after cutting. So now what you do is you take this part and then use that as a purely an attractive potential. So that is shown here. Okay, and the mathematically what is shown is that for R less than R minimum, the potential is minus epsilon. So that is this is minus epsilon here. And then after that, it is a function of R goes through this. So you can see that this particular potential is always negative. That's why this is an attractive Lennard-Jones potential. So now in the context of whether you want purely soft repulsive part or just only attractive part, you can either choose this or this respectively. Okay, so this addresses to purely repulsive, soft repulsive potential, and this addresses to a long range attractive potential. The other situation involves dealing with charges and ions. So in that cases, we use Coulombic interactions, and you know this form. This ZZ here basically means Z are the charges. This is a charge-charge interactions of species I is given by Zi. Zj is the charge on species J, and then this R here is the distance between the two ions, and epsilon here is the permittivity of free space. So you can account for charge or electrostatic interactions using Coulombic form. And dealing with the charges are a little tricky in the sense the ions can also, the charges and ions can also induce polarizability in the neighboring molecules or neighboring particles. So there are certain methods called core shell model, which will account for polarizability also. Okay, but we don't want to go beyond this this point further discussions. But I want to just put it out there that it is not very simple Coulombic charge-charge interaction, but there is also other effects we have to bring in via polarizability. So now, so far, what we talked about is interaction between atomic systems, which can be modeled as spheres, and then we looked at the various Lennard-Jones potential and hard-sphere potential and very other idealized potentials, and also a point like a charge-charge interactions. But now when you move to molecular systems, and molecules are basically atoms bound together via chemical bonds. So now how do we handle molecular systems in MD simulations? So here we have various methods to handle it. We will go from very simple to more advanced levels of models. So the most simplest description you can have about molecule is to treat the molecules as some rigid or semi-rigid unit without really worrying about the variation of bond length and bond angle. For example, if you consider a diatomic molecule, okay, something like nitrogen or oxygen, so two atoms bound by a chemical bond, and this bond here will be fluctuating or undergoing vibrations with a very high frequency, but the amplitude with which these vibrations happens are going to be very, very low. So they don't contribute much on the dynamics of this system. So what we can do is we can actually approximate or model a diatomic molecule as a simple dumbbell with a fixed bond length. Okay, so you don't have to worry about how the bonds vibrate or how the bond length varies. You just think of two atoms connected by a rigid rod. Okay, that's what I call this as a dumbbell model. So people have done such diatomic molecules using a dumbbell model. And if you have so in the example here I've given here is, so if you want to go beyond, you can also look at these molecules like nitrogen, fluorine and chlorine, which are all like diatomic molecules. So these molecules have been modeled by fusing two Lennard-Jones atoms by a fixed bond length. So that is one, the example is shown here. So you have one atom in this position and another atom in this position, and they are actually bound by a bond, rigid bond, and there is a size given to each of this atom by fusing two Lennard-Jones particle close to each other. So this whole thing acts as a one unit. So this whole thing is a one rigid unit. So now you ask how to calculate interaction between two such dimers or a dumbbell. Then all you need to do is use this site-site approximation or atom-atom approximation, where in the ith molecule there are two sites, A equal to 1 and A equal to 2. In this molecule J, there are two sites, B equal to 1 and B equal to 2. So they are basically identical molecules, and we want to look at what is the pair interaction between them. So all you need to do is you basically sum over all the pairs. So A1 to B1, A1 to B2, and then A2 to B1 and A2 to B2. So you sum over all possible combinations, and that is mathematically written here. So you go to ith molecule and jth molecule, and then sum over all the sites. In this case, we have only two sites, but you may have any number of sites. And similarly, for the other molecule also, you sum over all the sites B1, B2, B3, etc. where this RAB here is the distance between those sites A and B between the molecules I and J. And this is one way of accounting for a molecular species using a rigid bonds and using this side-side summing of potentials. Now, if you look at how charges are to be distributed in a molecular system, so previously we talked about interaction between point charges or point ionic species using Coulombic interactions. But now when you have charges on a molecule, so these are not like fixed charges. These are basically charges that are distributed along the molecules itself. And again, there are different ways to do this. I'm going to give two examples of how charges are distributed on a molecule. The first one is on nitrogen, which is basically a diatomic molecule. So you can see there is one nitrogen here, another nitrogen here. It is fixed by a fixed bond like we discussed before. Now in this case, in this particular model, 5 partial charges are distributed along the length of the molecule. So there is some charge at the center of the bond and some charges at the center of the either atoms, and then 2 more charges slightly shifted away from the center of the particles. Okay, so you can see these are basically shifted from the center by some amount. The dimensions are given here. The distance between the center of the bond to the center of the atom is given here, and similarly the distance between this and this is given here, and then the charges Z and Z prime are given as well here. So as you can see, it's quite complicated, but having such a distribution of charges basically enables prediction of experimental results very closely. And in this case, if you have another nitrogen molecule, so you'll have a similar kind of situation. So there are charges in the midpoint at the center of the atoms and also slightly shifted here. So what you will do is you will take this particular charge and then you sum over the interaction between this charge and via with all the other charges here. So this is what side-side approximation means. Once you are done with this charge, you will move to this charge and do this all over again. So you can see that if you have many number of points, sites, and then when you are looking at the point charge-charge interactions, then you see that this number of summation that you have to do also goes up. And then similarly, if you look at methane, so methane is actually a tetrahedral molecule. So there is a carbon at the center here, and then 4 hydrogens. And the way the charges distributed here are, so some minus 4 Z charges are in the carbon, and then Z charges are in the 4 hydrogens on the tetrahedral points. Okay, and the magnitude of charge is given here. So you can see that within the molecule they are electron neutral, but then between the molecules you can always sum over all the charge side-side charges and then sum over the interactions. So that's what I have mentioned here. The interaction energy between partial charges on different molecule is summed over all the side-side interactions. So now if you extend this approach that I can take any molecule of any size, and then I should be able to put charges, and I should be able to make fixed bonds and then fuse the atoms together in a certain fashion. And you can go about this, but the problem you will see at some point of time is that the number of sides to represent each molecule becomes so large that when you try to do this pair-pair interactions via side-side approximation, then you will have a huge computational load in doing such calculations. So at that time people were thinking about, is there a better way to do this instead of using side-side approximations. So the example is given here. Suppose if you take ethyl benzene, okay, so it has this benzyl ring and then there is a ethyl group, and then if you try to visualize how this molecule look like, it has this ring in this plane, and then there's ethyl group on the so this is the ethyl group and this is the benzene ring. Okay, and topologically it is shown as a fusion of 2 objects, one elliptical object representing the ring and another elliptical object representing the ethylene group. So what was considered in this problem is that think of this molecular species as a non-spherical soft object. Instead of looking at the details of individual atoms and sites and charges, you think of them as a soft non-spherical object and then represent them and then try to calculate the interaction energy between them. So the way you can do that is the shape itself is modeled as a overlapping Gaussian functions. It is a little bit mathematically involved, but what I'm trying to tell you here is that it is possible to model a large molecule not via atom specific details, but looking at the overall shape of the molecule without really worrying about the internal motions and internal dynamics. So you look at overall topology of the molecule and then construct a shape, a soft shape to represent the molecule, and then the interaction between them can be calculated using set of overlapping Gaussian functions. And then finally what happens is that the interaction between such objects, non-spherical objects, will depend on the orientation also. If you remember the Leonard-Jones potential between spherical particles, there is no orientation dependence. It only depends on how far two molecules are apart from each other. Okay, there's only r, that is a variable. But when you have non-spherical particle, then depending upon the orientation, the interaction could be different. So for example, in this case, two ellipsoids are coming side by side. In this case, two ellipsoids are coming along the tip to tip. So depending upon this orientation, the interaction energy also will depend on. So now for interaction between non-spherical molecules, not only the pair distance is important, but also the orientation, relative orientation also important. To encode all these things, what you can do, you can use Leonard-Jones with the change or with the correction that both the energy parameter epsilon and the sigma parameter sigma, both of them are dependent on the orientation of the molecule itself. Okay, whereas in the simple Leonard-Jones, epsilon and sigma were the parameter for a given system. They do not depend on the orientation. But then when you adapt the Leonard-Jones potential for the non-spherical molecules, then this epsilon and sigma can be written in terms of the orientation itself. This parameter epsilon here is defined using the orientation ui and uj of the respective molecules. So ui, uj are the, for example, in this particular molecule, ui and uj are here. That tells you the orientation vector of the molecules. And chi here is the parameter that tells you about the anisotropy of the molecule. Okay, so you can see that the chi depends on some two parameters, sigma parallel and sigma perpendicular, and it tells you the anisotropy or the aspect ratio of the atom or the molecule, and relates to its non-spherical shape. And similarly sigma, which tells you about the size, it also depends in a complicated manner via this equation. You can see that what goes in this particular expression is this interparticle distance, scalar distance, the anisotropy parameter chi, and also the relative orientation ui and uj. Okay, so so the way you will do this in a computer simulation is, at any given instance, if you want to calculate pair interactions, you take two molecules, find out what is the distance between them and what are the orientation at that moment, and then you calculate the epsilon parameter and sigma parameter, use them in the Leonard-Jones expression to get the energy, and then you sum over all the pairs. So it's quite a little bit complicated, but it's very effective compared to an equivalent site-to-site model. Now, and then in this example, the butane, N-butane is actually was modeled, and the way it was modeled is, this is the butane molecule. You can see there is a CH3 group, CH2, CH2, and then CH3, and there are carbon-carbon bonds between them. Okay, so the way the N-butane is modeled in this particular study was to think of all these groups, CH3, CH2 as a single sphere, and these are the sphere. This is a CH3 group, this is a CH2 group, this is a CH2 group, this is a CH3 group. Okay, so they are all kind of combined together. CH2, CH3 are combined together as a one single unit, and they are connected by a rigid bond by certain length. So the bond lengths are fixed by some length, and also even the bond angle also. The bond angle also is fixed. That means this is a kind of a very the bond angle cannot fluctuate, bond length cannot fluctuate, so they are kind of semi-rigid in that sense. And you can see that the bond angle is fixed at 109.28 degrees, and the bond length is fixed at 1.53. The only thing that was allowed is a rotation about one particular bond. So that is shown here in this particular plane. So imagine that this is 1, 2, 3, 4 number for the atoms, and you can see that they are here 1, 2, 3, 4, and then about this bond between 2 and 3, and this molecule is allowed to rotate. Okay, and this rotation has a particular energetics. A certain configuration along the rotational axis has different energies. For example, in this case, when the angle, so the way you can think about this rotation is this atoms 1 and 2, 3, they are on this plane, and atoms 2, 3, 4 are in this particular plane. And then the angle between these two planes is given as phi. And then by changing this phi, you can see that there is a energetics to it. For example, if phi is equal to 0, that's where the energy is minimum. And then the moment it tried to rotate about it, there is a 2 minima which is symmetrically distributed. And then if it goes to pi or minus pi, the energy is very high. So that means along the rotational direction, the energy, there are 3 stable energy states which are given by this and this. So using this particular simple torsional or dihedral energetics, people have found that the properties of butane can be easily predicted to match experimental details. So the most important thing in this case is that the only thing that is required here is a torsional energy. The potential energy coming via only the torsional energy is important to predict experimental data, even though the grouping, fixing of the bond length and bond angle was considered in this particular case. So moving on, as of today or as of now, if you go to any MD simulation package like LAMS or GROMACS, you will see that you don't have to worry about building all this model. It's already done there for you. Okay. And for example, here I have taken a amber force field. There are many other force fields. CHARM is there, OPLS, and so on, so and so. And if you look at the manual of these potentials or force fields, they will give you a full potential mapping. What kind of functional form each forces are taken into. For example, in this case, in amber field, all the bonds are represented by a harmonic bonds. Okay, so there is an equilibrium bond defined for every bond in the system, and then anytime the bond contracts or expands, there is a penalty for energy. So those are bond energies. Similarly, the bond angle are also allowed to fluctuate about an equilibrium angle. It also takes a harmonic form. And then you have this dihedral or the torsional potential. So that is rotation about about a bond wherever there is a 4 set of atoms connected by bonds. And then you also have this Lennard-Jones interactions, charge Coulombic interactions, and this also have additionally hydrogen bonding interactions in the system. So when you take a molecule, when you want to simulate with the Amber's force field, you will be choosing different constants Kr, R equilibrium, K theta, theta equilibrium, and various other parameters Aij, Bij, particular to the particular atomic species. So here I have given an example. Suppose if you want to model a glycine as an amino acid with a molecular formula is here. So what you do is you try, so within the Amber's force field, you will try to map this molecule into a set of atoms. These atoms are specific to this particular Amber force field. So for example, this O connected to is represented by this O here, whereas this C group here is the COH group here is represented as C, and here there's NH2, one H is here, and this one will represent N and H. So you can see that it is possible to map atom to atom or group of atom to an atom, and you can see that each atom has a particular name. Here C and C2 are different, even though they are basically carbon based, but the chemical environment is different. So based on this Amber's force field, your job will be take your real molecule and then map onto a Amber force field specific naming and grouping of atoms. Once that is done, then your simulation software will take care of calculating the interactions and potential via this full potential. Now you might wonder, how is it possible to have all these constants and parameters available for all the systems, chemical systems? Well, that is because these parameters have been parameterized based on comparing with a lot of experimental data that is out there. For example, if you want to look at how partial charges are parameterized, these are coming from either quantum electronic calculations or some other spectroscopic methods. Similarly, Lennard-Jones parameters are optimized based on matching the lattice energy, molar density, and the enthalpy of evaporation. And the bond length and bond angles are obtained by matching spectroscopy and microwave structures, and so is the torsional parameters also. So, so we saw that in the beginning, very simple models, idealized hard sphere, soft sphere, square well, Lennard-Jones models, and then towards the end, we have seen what is possible for complete specification of all the inter and intramolecular interactions in a open source MD package. If you look at any other force field, you will see that similar form. Sometimes they will take a different form of Lennard-Jones, or a different form of torsional dihedral will be taken in the respective force field codes. So to summarize, the most important thing to remember about MD simulation is that the potential energy function to specify the model in the system is the key input that is required. And we also saw that the potential energies can be split into various components of unibody, pair body, two body, three body interactions. Of these, two body or pair interactions are the most important ones to be specified. And we also saw that as far as atomic systems are concerned, we can model them as spheres with the different degrees of softness and attractiveness. And in terms of molecular systems, we had a lot of possibilities and variations, ranging from very simple rigid dumbbell model for linear molecules with partial charges, or if you have a little larger molecule, the topology of the molecule can be mapped onto some non-spherical soft particles using a Gaussian overlap Lennard-Jones potential. And sometimes we can even take a simple molecule and make certain degrees of freedom frozen, like bond angle and bond length, and keep other degrees of freedom open, in the sense that torsional degrees of freedom was available. This was a case shown for N-butane. And finally, we saw that it is possible to encode all the interactions, intra and intermolecular interactions, by specifying all the components of bond length, bond angle, torsional, electrostatics, Lennard-Jones, and even hydrogen bonding. Everything can be also specified fully for a given molecules also. And we also saw that these the parameters in this full model are basically optimized based on certain experimental results, so as to reproduce the experimental results.